want to count the different ways to order n elements and the different ways to put n elements in k boxes. The amount of elements that fit on the boxes have to be perfect. What I mean with that is if I have 7 elements, I am going to try to put these 7 elements into boxes. In the first box fits 3 and in the second box fits 4, for example. But in here we will have many boxes. The only thing is that each box will have a different capacity, and the boxes have to fit exactly the amount of elements that we have. Also, I want to show the relation between these two things and the formula. And what I meant here with this relation? Well, turns out that the ways to order n elements is n exclamation mark, n or n factorial. And this is n times n minus 1 times n minus 2, and so on until we get here 2 times 1. So for example, the way to order 4 elements will be equal to 4 factorial, which is equal to 4 times 3 times 2 times 1. And here, how to put n elements into k boxes. Let's say that we have k boxes and the first box has a capacity of S1, the second box has a capacity of S2, the third box of S3, and so on until the k box has a capacity of Sk. We know that they have to fit perfectly, so if we sum all the capacities, that has to be equal to n. And if we have this configuration of boxes, then the ways to put n elements into these specific k boxes will be n factorial over S1 factorial times S2 factorial times blah 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 until Sk factorial. So the ways to put n elements into two boxes, one that fits k elements and the other one n minus k elements, is exactly this thing here. Also, if we have here A plus B plus C, and then we will have here the different ways that we can do to sum 3 elements to get n. Here I forgot to a factorial. So first, how to order n things. When we order n elements, we have n boxes. We have the first box, the second box, the third box, until we have n boxes, each of capacity 1, and to each box we have to put an element. In these cases, the box was just the space we put the first one. Then we have the second one, and then we have the third one. For the first box, or for the first element, we will have n options. After we do one of these n different options, then we can choose the second one, and for the second one we will have n minus 1 options. Then for the third one we will have n minus 2 options, and so on until we get on to the last one, that the last one have no options because he only have to go where it has left. And this is exactly the same as n factorial. Super n, or I don't know, incredible n. Go to the second part.
I'm going to continue here.
If I want to order n element, we can do these 2 steps. One, put them in the boxes, and 2, order the boxes. order n elements was n factorial. The way to put them in the boxes is what we want to know. The amount of order in each box, so we have the orders of the first box is n factorial, the orders of the second box is s2 factorial, and so on until sk factorial, which are each the orders of each boxes. And here is n elements in k boxes. This is what we want to know, how to put n elements in k boxes, and these are the amount of orders that we can put the elements in each of the box. And these are all the orders of elements. And if it is the same, if you convince yourself that it's the same to order n elements than to put them first in the boxes and then order each box separately, then this s has to be equal to n factorial over s1 factorial sk factorial. Yeah, it's really cool, right? Explanation. I have k boxes. The first one with capacity S1, the second one with capacity S2, and the last one with capacity SK. In each box, I think of them as little boxes. Here there are S1 little boxes, here there are S2 little boxes, and here are SK little boxes. And in each of them, I am going to put one element, one of the n elements. And the ways I do this is exactly n factorial. But now I don't want to count the order differently, so I have to divide by s1 factorial. So I forget the order of the first box, s2 factorial, I forget the order of the second box, and I go like that until forgetting the order of the k box. That is a kind of different explanation than this one, but more or less the same thing. Now, why this has to do with the formula I showed at the beginning? This is on the right-hand side. Now, on the left-hand side, and to multiply this, we go b times 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 b. That is bn. Then b times b times b times b times b times b times a. That is a times b power n minus 1. And we are putting here all these combinations of ways that we can have here. But how many different combinations we have? And maybe we go first with an example. Let's say we have a plus b power 2. A plus b, a plus b. We multiply b times b, b squared, b times a b, a times b. So we finish with this one and with this one. So a times b is ab, a times a squared. Let's move this a little bit. And now we sum, and we have a squared plus 2 times ab plus b squared. And this is what it gives us the formula. Why? Because a plus b squared, the formula was the 1, and with k is equal to... So, sorry, we have only 3 elements. Here we start with 0, and I think that was a mistake here. But here is okay. We have 3 elements when k is equal to 0, when k is equal to 1, and when k is equal to 2. When k is equal to 0, 2 factorial, 0 factorial is 1 by definition. It's like how many ways we can order 0 elements. 1, not doing anything. 2 factorial, and here over 2 factorial will be 1. A power 0 is A, so we have no A, and B, 2 minus 0 is B squared. So B squared plus, when k is equal to 1, we have 2 factorial over 1 factorial over 1 factorial, so it's 2 factorial. 2 factorial is 2 times 1 is 2, and here A 1, and here B 2 minus 1 is 1. So 2 times AB. And when k is equal to 2, here we have 2 factorial, here we have 2 factorial, they cancel each other, and here we have 0 factorial, which is 1. So all of this element is 1. Here we have A squared, and here we have B times 2 minus 2 is 0. We have exactly what we have here, using this formula and using what we know, that is just summing all elements. So after we see this little example, let's continue again. We multiply all of these elements and then we sum the result. But to multiply all these elements, we have to do all the combinations of these two things. To do all this combination, we will have here 1, 2, 3, n. So we have n positions, and we are going to fit this 1 choosing either this side or this side. So let's think of this as 2 boxes, and we can try to put 1 in one box or 1 in the other box, and then have all this combination. If we put if we put k elements here, then we will have ak power k, that is that the a is multiplying k times, and then the rest of the elements will go to b. So the rest of the elements will be b n minus k. And how are the different ways that we have this one? It will be the different ways that we can put n element into the first box, that is of order k, and in the second box is all the rest. So that is n factorial over k factorial n minus k factorial. How cool is that explanation? I don't know, I find it interesting. Now if we have a plus b plus c power n, so we have a plus b plus c, a plus b plus c, n times, and we have to do all the combinations here when we multiply, and then here we sum everything that we have here as a result. But again, here we have 1 n elements. We can put it either on the first, second, or third space. So we can have, if we put S1 elements into the first box, then we will have A power S1. If we have S2 elements into the second box, then we will have B S2. And if we put elements into the third box, we will have C S3. And what are the different ways that we can put S1 elements into the first box, S2 elements into the second box, and S3 elements in the third box? Well, it will be n factorial over S1 factorial, S2 factorial, S3 factorial. And we are going to sum over all of these, all the different ways. And why we are going to do all of this is because in the next video I want to explain or to do certain probability a deck of 60 cards, a deck of 60 cards. I want to pick 7, and I want that 3 of these 7 are of certain type from the 60 cards that are here. And to do this kind of probability, I need all of this, well, not the sum, but I need to know how different hands I can get out of picking of 60. I hope you had a great time listening to me. If you find it interesting, please
subscribe
and see you next time. Have a good day.